So, where did you get your toga?
I got it from Zeus's cavern. It's an original with really rare fabric.
How did they uphold it?
Well, actually, oh my God.
Something happening with the volcano!
What do we do?
Whoa.
I think everything's fine. It's okay.
Oh gosh. What
That
just
was-
happened?
I have no idea.
Okay, whoa. Well, the weather's actually pretty nice for a change. It's been pretty bad lately.
I know, right? Finally.
Oh my God.
Oh my gosh.
It's happening. Oh my God, what do we do?
Whoa! Whoa! Yeah! OMG! Check out this baby!
What happened?
I don't know, but this is such a cool rock. Dang, look at that! Would you guys like to learn more about this rock? I can show you in my lab.
Sure.
Yeah! Let's go! This way. Yes. So good. Yes. Yes. Do you guys have any questions about these rocks?
I guess.
Surely inspired me to work in my field was actually I had just applied to go to a graduate program in history here at CU. And I was roundly discouraged from pursuing a history degree by all my former history professors because they were sort of disgruntled at the fact that they had joined up during the Cold War and there was a lot of money for China and Russian studies, and there wasn't any money anymore, and so they weren't very much into it. And it started raining as I walked back to my truck on this side of campus, and I went inside the nearest building, and the nearest building was the Geology building, and so I started looking around at all the wonderful rocks that are on the atrium. And I was like, why did I never think of doing this before? This is so cool. And then I actually started meeting some of the geology faculty members, and they were just the most lovable, biggest, wonderful nerds that I had ever met in my life. And they adored what they did, and they just wanted to share it with everybody, and that totally sold me. That was the life that I wanted to have too. Well, so the rocks that I study right now are all from very, very deep in the earth, like 30 to 40 kilometers down. And they were all very hot at one point, and they were all sort of squishing like silly putty does when you rub it between your hands. And so they were flowing in what we call a plastic sense because they were so hot and they were so deep. But the rocks that I study specifically are in those rocks. They're littler rocks in those rocks, the plastic rocks. And they are these black veins of molten material that happens when an earthquake rips down that far into the earth. And the amount of friction from the surface of the earthquake grinding on itself is so much the temperature goes really, really high, really, really quick in the earthquake fault plane, and you get like a flash melt all up and down the earthquake fault. And so then you can find those later as fossil earthquakes, which are these black sort of melt veins. Well, they are super hard to find out in the field, as we say, because they are usually this big, and they're usually in a rock that was flowing in a certain direction, right? And so those rocks tend to have black lines in them, and white lines, and black lines, and you have to try and find the one black line that's different from the other black lines. And sometimes you'll spend all day looking at these stripy rocks, and being like, oh, that's one, and be like, oh, no, that's the shadow of a twig. They'd be like, oh, that's one, and be like, oh, no, that's some dirt. But sometimes you can find them, and then they're really cool. Could I? I could definitely show you some samples. So, such as this rock from Pompeii that we picked up. What you do with a rock like this, when you get it from the earthquake area, right? Say that it came to the surface after having an earthquake. You can take a rock like this, and you can put it in some saws that we have, and you can cut it into a little rectangular prism, basically just a little rectangular box, of rock. And then what you do is you take that rectangular box, and you put it in a special machine that saws really, really close to one edge of the box. And so then you have a little wafer of rock, basically. But the wafer is still too thick, because what you want is for the rock slice to be so thin that you can look through it with some light. So then you take your little rock wafer that's still too thick, but it's still really thin, and you put another special machine that holds it really, really carefully, and then just slowly will start grinding it down gently until it's so thin that light goes through it. And then you take it and you stick it to a piece of glass so that it don't break, because it's so thin it'll break so easily. Oh my god. And what you do is you end up with piece of rock, like a slice like this. Maybe you can see it better with the white, like that. And you can see in there how there's like it's clearly like a shattered piece of rock with all the black stuff in between. The black stuff is the melt from the earthquake. And obviously an earthquake is like a violent thing, and so it shattered the rock and melted part of it at the same time. And so then, once you have your little slice of rock, you can take it and you can put it in a microscope, like so. And then there's a camera on the microscope, and then the camera talks to the computer, and you get this cool image of the smashed up rock that you can go sort of drive around on and be like, oh, look at that thing, that's so cool. Wow, look at that. Oh, it's so close. Such good magnification. And then you can learn stuff about it. Yes, look at that giant pyroxene glass. Oh, that's the best. Oh, and look at this weird diorite nodule. That's what I'm talking about. Oh, and the vesicles. The vesicles in this thing. Amazing.